So, good evening and welcome back to this live problem solving session for the NPTEL course Geology and Soil Mechanics. So currently we are at the end of week 11, and in the last 2 weeks we solved a few numerical problems based on shear strength of soils. Now in this week we have proceeded further, and we have learned about another important aspect of soil mechanics, that is earth pressure theories. Okay, so under this topic we have learned what is earth pressure at rest, active earth pressure and passive earth pressure, and determination of these earth pressures, active and passive, for various backfill conditions like dry backfill, submerged, inclined, and so on. So using two well-known established theories, which are Rankine's theory of earth pressure and Coulomb's theory of earth pressure. At the same time, while we were determining the earth pressure in cohesive frictional backfill or in cohesive backfill, purely cohesive backfill, we have seen that there is a chance of generation of tension crack at the top surface of the backfill. And from that concept, we have derived the critical depth of a vertical curve, which is composed of purely cohesive soil or maybe cohesive frictional soil. So, with this uh, short recap of week 11, we'll basically start solving a few problems regarding all these aspects of earth pressure theory. Okay, so in this week we'll solve a few problems, and in the next week, that is in 11, week 12, so we'll be solving the remaining problems. Okay, so this is our first problem for this session, and in this problem we have to calculate the total active charge on a vertical wall which is 4.5 meter high, and retaining a sand of friction angle 30, angle of internal friction 38 degree, and unit weight 16 kilonewton per meter cube. So this retained sand is having a horizontal surface, top surface, and the water table is seen at the far below the bottom of the wall. So this is the field condition for which we have to determine the total active charge on the vertical wall. Okay, so first we'll draw the problem geometry. So this is the retaining wall. This is the retaining wall, and the height of this wall is 4.5 meter. So this is 4.5 meter, and it's retaining a sand of horizontal top surface. Okay, so what are the properties? Yes, some properties of the sand. Angle of internal friction is 38 degree, and the unit weight of the sand is 16 kilonewton per meter. And there is no water table located at least within the height of the retaining wall. Okay, so it's below the bottom of the wall. So that's why it will not create any problem in the calculation of, or it will not come into the in the picture of calculating the active thrust on the wall. Now, as you know, so this important relationship, that sigma 1 equals to sigma 3 tan square 45 plus 5 by 2. Okay, so it will be better written in this fashion, sigma 3. Okay, no, let's do it in this fashion only. Sigma 3 tan square 45 plus I by 2 plus 2c tan of 45 plus 5 by 2. Okay, so this is the relationship between the major and minor principal stresses on the verge of failure, and here this I and C are nothing but the shear strength properties of the soil medium. Okay, now from the concept of active earth pressure, so you should know at least this part. Okay, so from the learning of this specific way, that your sigma 3 would be the passive earth pressure, or sorry, active earth pressure, and sigma 1, this will be the vertical overburden, and obviously effective vertical overburden. Okay, so it will be better if we write in this fashion. So sigma 3 is nothing but the horizontal stress, and sigma 1 is nothing but the effective overburden. Okay, now if we rewrite this equation for sand, so for sand, this equation would be sigma b prime. And what is sigma b prime? So sigma b prime, if we try to take the reference at the top surface of the backfill, if J is measured from the top surface of the backfill, so sigma b prime, it will be gamma times J. Gamma is the unit weight of the medium backfill, and Z, this is the vertical depth at which we are interested to calculate the active earth pressure. So this gamma, so this we should take the submerged unit weight. Okay, since we are calculating the effective overburden pressure. Now for this case, since the sand is at completely dry condition, so the whatever unit weight which is given to this problem, that will be the submerged unit weight. Otherwise, you have to take the difference between saturated and the unit weight of water. Okay, so to get the submerged unit weight of the backfill material. So sigma v prime, so this we can write as gamma z equals to, okay, again sigma h, this is the passive pressure. If we use active earth pressure, if we use a different notation, so it will be PA tan square 45 degree plus 5 by 2, and remaining part will be 0, because for sand the C value is 0. Okay, so there will not be any correction. So therefore this PA, this will be gamma z tan square 45 plus 5 by 2, and this you can write it as KA, that is the active earth pressure position. So PA will be KA. Okay, so this is the variation of active earth pressure with Z. So as you can see, for the given backfill condition, so what are the backfill conditions? The backfill is sand, it's having a horizontal surface which has no inclination, that is top surface is horizontal, and the sand is and completely dry condition. So these are the active conditions. Now for these active conditions, as you can see that the active pressure will vary linearly with the height of the retaining wall. So that means we will be having a variation like this. So it will start from 0 at the top of the backfill and it will reach up to a value Ka gamma times H at the base of the wall. So at the top of the wall, it will be having a value 0. Then it will start varying linearly with the height of the wall and it will reach a value of K times gamma H at the base of the wall. So from the simple geometry, so if we try to find out the active thrust, total active thrust, so it will be the area of this variation, this triangular variation or linear variation. So we are getting a triangle, okay. So it will be half times K gamma H plus H. So that means half K gamma H. Okay. So this is the total active thrust which is acting on the retaining wall, backface of the retaining wall. Okay. Now okay, so whatever value for the active total active thrust or the variation of this active pressure we have obtained, so this is on the basis of Rankine's arc pressure theory. Okay, so that you should please keep in mind that this variation or this value is on the basis of Rankine's arc pressure theory. Okay, so now we have got the expression for total active thrust on this particle wall. So we have to just substitute the appropriate values in this expression and we can get the required value. Okay, so for this problem your gamma is 16 kilonewton per meter cube, then H 4.5 meter, and what is K? So this is the active arc pressure coefficient. This is active arc pressure coefficient. Okay, so based on Rankine's theory and its tan square. Okay, so let me correct this equation, because if we take this tan square 45 plus 5 by 2 in this side, so it will become tan square 45 minus 5 by 2. So it will no more plus 5 by 2. Okay, so it will be on the denominator. So 1 upon tan square 45 plus 5 by 2, that will become tan square 45 minus 5 by 2. So therefore, this active arc pressure coefficient, so this is tan square 45 minus 5 by 2. And for this problem, phi value is, what is the phi value? Phi value is 38. So tan square 45 minus 38 by 2, so it's 0.238. Okay, so therefore the total active thrust would be half into 0.238 into 16 into 4.5. So 38.56 kilonewton per meter. Okay, so you can start from this expression also. Okay, so directly you can start from this expression, that you know the variation of active earth pressure with Z, and that is nothing but K times gamma Z for a questionless soil deposit, dry questionless soil deposit, and the top surface of the deposit is perfectly horizontal. There is no inclination and there is no water table. So you can start solving this problem directly from here. Okay, so where gamma is the unit weight of the backfill, Z, this is the depth from the top surface of the backfill, and K, this is the earth pressure coefficient at active condition. Okay, so by that time you should know these definitions. So what are the definitions of active earth pressure, passive earth pressure, and earth pressure at rest? So I am not going into that details because it will unnecessarily delay our session. We have a lot of numerical problems to solve in this session. So for the theoretical or from the for the definitions of these pressures, active, passive, or at rest, so I'll request all of you, please go through the video materials or the lecture materials which are uploaded on the portal. Okay, so then it will be easy for both of us. Okay, so if it is okay, then we can take the next problem. Next problem is a slight modification of this problem only. So in the next problem, so we have to determine again the active thrust on the wall, which is given in problem 1. However, in this case, the water table rises to a level 2.5 meters below the surface of the sand, and we have to consider the saturated unit weight of the sand as 19 kilonewton per meter cube. Okay, so unlike the previous problem, so in the previous problem we didn't consider any water table. So as I mentioned earlier, that water table has an effect on the earth pressure, so whether it's active or passive, that we'll see how the water table, how does the water table impact the active earth pressure to this problem. Okay, so this is the height. Now the water table is located at a depth of 2.5 meters. So this is the water table location, and below this water table the sand will be saturated. So for that we have to use the saturated unit weight, and which is given as 19 kilonewton per meter cube for this problem, and above the water table will use this unit weight only. Okay, So you can refer this unit weight as the bulk unit weight. 16 500. And the shear strength parameters will remain same. So C is your 0 and phi is 30 degree. So shear strength parameters will not change. Now if shear strength parameters are unchanged, therefore the active earth pressure coefficient, it will also not change. So it will be 0.238 only. Okay. Now, as I mentioned earlier, that you have to be very careful about the overburden pressure, because you have to always consider the effective overburden pressure, not the total overburden pressure. Okay, effective in the sense total minus the pore water. Okay, or in other words, you have to consider the submerged unit weight. Okay, so this effective overburden pressure you can calculate in two ways. In the first case, so you can calculate the total pressure, you can calculate the pore water pressure, then you can deduct the pore water pressure from the total, so you can get the effective pressure. Now in the second approach, you can directly calculate the effective overburden pressure by multiplying the submerged unit weight with the corresponding height or thickness. Okay, suppose h. So we'll use the second one because it's a straightforward and it will save our time. Okay, at least for the from the examination perspective. Okay. Now, as you can see that from, okay, so let me calculate the pressures in this fashion. So as we know that the variation of active earth pressure is Ka gamma Z. Okay, K value we know, gamma will consider depending on the water table location. So if the soil is above water table, so we'll use 16 kilonewton per meter cube. If it is below water table, then we'll use submerged and submerged unit weight. So we can calculate here the submerged unit weight gamma prime. So this is gamma sat minus gamma w. That means 19 minus 10, 9 kilonewton per meter. Okay, so this is the submerged unit weight that we'll use for the backfill, which is below the water table. Okay, so now we'll consider three locations. So first of all, at z equals to 0, so at z equals to 0, what is your PA? So PA is simply 0. Then z equals to 2.5 meter. What is your PA? Active earth pressure. So this is 0.238 multiplied by 16 multiplied by 2.5. Okay. So it's 9.52 kPa. And z equals to 4.5 meter. Your A would be 16 into 2.5 plus 9 into 2. So this would be the effective overburden pressure at the base of the wall. Okay. So for soil above the water table, it will be simply 16 multiplied by 2.5. But below the water table, we have to take the submerged unit weight only. So that's why we have taken 9, and that would be multiplied by the remaining depth, that is 2. Okay, because the wall is having a total height of 4.5. Now out of this 4.5, 2.5 is dry or above water table and 2 under water table. Okay, so this multiplied by 0.238. So this is the soil. This is due to the soil. Now due to water, you will be having we will be having this active pressure, and that will be simply gamma W into Z. Okay, now this Z, the reference for this Z, you have to take from this, from the water table location only. So you will be having something, this kind of linear variation. Okay, so this additional water pressure you have to consider, and that will be gamma W times Z, and that Z or Z prime, that Z prime will be calculated from the water table location only. So gamma W you can take 10, and for this problem, that is at the base of the wall, this height is 2 meter. So 10 multiplied by 3. Okay, so we'll calculate in a part by part fashion. So the first component will be 16 into 2.5 plus 9 into 2 multiplied by 0.238, that is 13.8. Now the core water pressure component, this is 20. So that means 33.8. Okay, now if we draw the distribution diagram, active earth pressure distribution diagram, so it will look like this. So this is up to 2.5 meter. This is 2 meter. Okay, so this figure is not in scale. So this value is your 9.52. Okay, the gradient will be different. So what is the value at base? It's 13.8. So it's 13.8 plus the water pressure. Okay, so water pressure will be only for the lower 2 meter height, and this is, so this is the active earth pressure distribution diagram in KP. Okay, so now if we try to calculate the total active thrust, because this is the objective for this problem, the total active thrust which is acting on the wall, the total active thrust will be the summation of this individual components. Okay, so if we split this entire distribution into the regular geometries in the sense triangle, rectangle, so we can calculate the area of that geometries, and we can then take a sum of all the areas, so that will govern the total active thrust, which is basically acting behind the wall or at the back face of the wall. Okay, so now this is your one component, this is your two component, and this is your component 3. So for component 1, so it's a triangle, So the area would be half times 9.52 times 2.5. So this is your component 1. Then component 2, so it's a trapezium, so it will be half times 9.52 plus 13.8 multiplied by 2. So this is your component 2 plus the third one, which is half 20, this component. Okay, so if we calculate, then it will be 9.52 into 1.25 plus, so it's 11.9 plus 9.52 plus 13.8, it's 23.3 plus, so 55.2 kilonewton. Okay, so this is the, therefore to obtain the resultant active thrust on the wall, it's very important to have a knowledge about the active earth pressure distribution diagram for the wall. So if we know the active earth pressure distribution diagram for the wall, so we can easily calculate the total active thrust by splitting the distribution into regular geometries and then taking the area of them, and finally taking the summation of all those areas will give you the total active thrust behind the wall. Okay, so this is all for problem 2. So as I mentioned earlier, so this is a modified version of problem 1. So we have dealt with the same retaining wall of height 4.5 meter, which is retaining the same backfill material, that is sand, having angle of internal friction 38 degree. However, in the first problem, there was no water table inside the backfill, and in the present case, there is a water table at a depth of 2.5 meter from the top surface of the backfill. Now, due to this water table, what will be the change in the active earth pressure, total active thrust, that we have calculated in this problem 2. And if we make a comparison between the two pressures, active thrust to total active thrust calculated in problem 1 and problem 2, then we can easily see, so there is a rise in the total active thrust due to the inclusion of water table inside the backfill. Okay, so this water table will basically give added pressure on the wall, and that is quite obvious from the practical perspective. Okay, so if it is okay, then we'll move further and we'll take the next problem. So in this problem, a rigid retaining wall of 5 meter height has 2 layers of backfill. Okay, so in the first two problems, we have dealt with only one layer backfill condition configuration. That is, the backfill is basically the retaining wall is retaining only a homogeneous backfill. Okay, having uniform shear strength parameters, the parameters which are uniform or constant throughout the depth or height of the backfill or retaining wall. However, in the present problem, as mentioned, that this rigid retaining wall, which is having a height of 5 meter, has two layers of backfill. Okay, now we'll see what are the properties of this backfill. So the top layer to a depth of 2 meter is sandy clay, and it's having the angle of internal friction 18 degree, cohesion 15.12 kPa, and the unit weight as 16.8 kilonewton per meter cube. And for the bottom layer, which is sand, having angle of internal friction 32 degree, cohesion 0, and the unit weight of the sand is 17.5 kilonewton per meter cube. So for this problem, we have to determine the active earth pressure acting at the bottom of the wall. So please be very careful. So in the earlier two problems, we have calculated the total active thrust acting on the wall. However, in this problem, we'll be only calculating the active earth pressure at the bottom of the wall. So we'll not calculate the total thrust. Okay. So however, we can calculate if we know the distribution, but that is not required for at least for this problem. Okay. So we'll first visualize the problem definition through the problem sketch. So this is the rigid retaining wall, and it's having a height of 5 meter, and it's retaining two layers of backfill. First one is having a thickness 2 meter, so obviously the second layer will be having a thickness 3 meter. Okay. Now the first layer is sandy clay, that means the top layer, and the bottom layer is sand. Now coming to sandy clay, the angle of internal friction is 18 degree, C is 15.12 kPa, and gamma is 60.8 kilonewton per meter cube. Now for sand, your angle of internal friction, that is phi, is 32 degree, cohesion is 0, and unit weight is 17.5 kilonewton per meter cube. Okay. Now we have to calculate the pressure, the active earth pressure, which is acting at the base of the wall. That means at a depth of 5 meter on the top surface. Okay. Now from the problem definition, it's quite obvious that since the backfill is not uniform, or the backfill is not homogeneous throughout the height of the wall, the properties are basically varying from layer to layer. So it's a layered backfill case. So obviously we'll be having two active earth pressure coefficients. Okay. So unlike the previous two problems where we have only one earth pressure coefficient throughout the backfill, however in this case we'll be having two active earth pressure coefficients. So one is for the top layer, that is sandy clay, and another one is for the bottom layer, that is sand. So we'll first calculate what are the values of this active earth pressure coefficients. Okay. So if we introduce two notations K, A, 1 means the first layer, okay, top layer, and K, A, 2 means the bottom layer or the second layer. This will represent the active earth pressure coefficients for the two layers, okay, which are given to this problem. Now for the first layer, your active earth pressure coefficient would be tan square 45 minus 18/2. So it's uh, 0.528. It's for the top layer, okay, or sandy clay. Now coming to the bottom layer, the active earth pressure coefficient would be 45 minus 32 by 2. So it's 0.307 for sand. Okay, so we have calculated the active earth pressure coefficients for both the layers. Now we'll proceed for the variation. So this would be the variation. Okay, so again this will come from the fundamental relationship between the major and minor principal stresses on the verge of failure. So in the very beginning problem, we have discussed a little bit about this. Now in that problem, since we were dealing with sand, so we have neglected the second component. Now if we didn't neglect the second component, that is the cohesion component, since the soil was sand, so that's why we neglected the second component. However, if this is not the case, so as we can see for the present problem, this is not the case. So cohesion will be there, at least for the top layer. So therefore, this will be the complete expression or the final expression for the active earth pressure variation throughout the height of the wall. Okay, so this second component will be there due to the cohesion. So gamma zk minus 2c root. Now, as you can see that if we consider the case of z equals to 0, which indicates the top of the backfill or top of the retaining wall, so what will happen? The PA value would be simply minus 2c root under k. That means your pressure becomes negative. Now what does it indicate? The pressure is having a negative value. It indicates the top of the backfill is under tension. So since we consider the compression as positive, so negative value will indicate that the top of the soil or top of the backfill is under tension. Now, up to what extent this tension will be the prevailing condition? So that we can determine by equating this PA, this PAZ to 0. Okay, so where the sign change is basically occurring. Okay, so where the sign change occurs, that we can determine by solving this equation PA equals to 0. Now from this equation, suppose we are getting the value of Z as Z0. Okay, now this Z0 is nothing but the depth of tension grad or the tension zone. This is the depth of tension crack zone. So therefore, in the cohesive frictional soil, unlike the purely cohesionless soil, in cohesive frictional soil, so there will be this generation of tension crack in the top portion of the backfill. Okay, so up to the extent z equals to z0, and this z0 we can calculate. Okay, so we can calculate. So if we equate this equation, this PAZ to 0, so what will happen? So we'll get gamma z0k minus 2c root k equals to 0. That means z0 will be 2c upon gamma multiplied by root under k. So this is the value for tension crack depth. So up to this z0, so there will be the tensile pressure. Okay, so due to that tension, the soil will not be in contact with the retaining wall. That we'll see in the subsequent problems, because this is not the concern of this present problem. In this problem, we have to just calculate the active earth pressure which is acting at the base of the wall. Okay, nothing more. So we have seen that in the case of cohesive frictional soil, so there is a chance of generation of tension at the top portion of the soil, and up to what extent this tension condition will prevail, that also we have determined. So from this expression, the tension crack depth expression, and this depth of tension crack will be 2c upon gamma multiplied by root k. So all these parameters we know. C is cohesion, gamma is unit weight of the backfill, and k, this is the earth pressure coefficient at active condition. Okay, so we can easily calculate. Then we can easily calculate the depth of tension crack. Now after this depth of tension crack, there whatever pressure will be getting, that will be under compression. Okay, so then we'll start calculating the variation. So at z equals to 0, so we have seen that PA will be simply 2c root under Ka. So 2 multiplied by 15.12. This is the cohesion of the top layer, multiplied by root under 0.528. So this is the active earth pressure coefficient for the top layer. So it would be minus 21.97. Okay. Now we'll calculate the tension crack zone, the depth of tension crack. So which is nothing but 2c by gamma root k. So 2 into 15.12 by 16.8 multiplied by 0.52. So it's 2.48. Now what we can see that the thickness of the top layer is only 2 meter, and we are getting the depth of tension crack is 2.48 meter, so slightly greater than the thickness of the top layer. So therefore the entire layer will be under tension. Okay, so if this is the tension crack, entire layer will be under. Now we have to calculate the value of active earth pressure at a depth of 5 meter. Okay, so for that we have to first calculate what is the effective overburden pressure at that depth. The effective overburden pressure at that depth would be 16.8 multiplied by this thickness 2 meter plus 17.5 multiplied by this 3 meter. Okay, so that will give you the total overburden, effective overburden pressure at the base of the wall. And again, since there is no water table, so we are taking this unit weight. This is as the submerged. Okay, so submerged and total, that will be the same. So 16.8 multiplied by 2 plus 17.5 multiplied by 3. This multiplied by the active earth pressure coefficient is K. Okay, so this portion is your gamma Z. This portion is your gamma Z portion. Now that gamma Z you have to multiply with Ka. Now what is the value of Ka? So for the second layer, so this will be 0.307. So 0.307 minus 0, because the second layer is sand, so C value is 0. Okay, so this part will not be there for the second layer of the backfill. Okay, now if we calculate, so it will be 26.43 kilonewton per. Okay, this will be the answer. Now in this problem, since we have to only calculate the active earth pressure acting at the bottom of the wall, there is no need to determine the entire active earth pressure distribution for the entire height of the wall. So that is not needed. If you were asked to determine the resultant active thrust, which is basically acting on the wall, in that case you have to first establish the entire active earth pressure distribution for the wall, and then you have to take the summation of these individual areas to get the final or the total active thrust. Okay, So we can continue, we can extend this problem further to calculate the resultant thrust, but that will not do for this problem, since we have other few problems. So that will do, and in that case we'll try to calculate the resultant active thrust if required, because already we have seen how to calculate the resultant active thrust through previous two problems. So in this problem, our objective was only to calculate the active earth pressure at the bottom of the wall. Now, the first few things which we have discussed, that is the generation of tension crack for a cohesive frictional backfill in the top portion of that backfill, and how to calculate the depth of tension crack. That was solely to uh, for the purpose of our subsequent problems. So in the subsequent problems, we'll encounter this type of configuration or this type of backfill condition frequently. So for that case, or in that case, it will be easy for us to easily calculate or easily understand whether there is a chance of generation of tension crack or not, or if yes, so if there is a chance, then how to calculate the extent of the tension condition or the depth of tension crack. Okay, so this calculation will assist us in future if we encounter this type of cohesive frictional backfill. Okay, otherwise we can directly solve this problem by calculating the active earth pressure coefficients for the lower soil, that is sand, and by calculating the effective overburden pressure at a depth of 5 meters. Okay, so we can directly start from here. Now we'll take one problem from GATE examination 2020. So in this problem, a 5-meter high vertical wall has a saturated clay backfill. The saturated unit weight and cohesion of the clay are 18 kN per meter cube and 20 kPa respectively. The angle of internal friction of the clay is 0. In order to prevent development of tension zone, the height of the wall is required to be increased. Dry sand is used as backfill above the clay for the increased portion of the wall, and the unit weight and angle of internal friction of sand are 16 kN per meter cube and 30 kPa respectively. Assume that the back of the wall is smooth and the top of the backfill is horizontal. To prevent the development of tension zone, the minimum height by which the wall has to be raised. So this is a very simple question. So for that, to answer this question, we have to have a concept of tension zone or the tension crack that we have already discussed in the previous problem, and we'll see the application of that concept through this numerical example. Okay, so two scenarios are mentioned in this problem, so we'll discuss them one by one. So for the first case, there is a retaining wall having a height of 5 meters. Okay, and what are the properties? Saturated unit weight is 18 kN per meter cube and cohesion is 20 kPa, and the phi value is 0. Now obviously, since this is a purely cohesive backfill, there should be a depth of tension crack, but in reality we don't require that tension zone. Okay, now one of the as one of the preventive measures, it has been discussed that will basically increase the height of the wall by sand filling at the top portion of the wall. So this is the increased height. So suppose this is your H and this is your sand. Now what are the properties of this sand? Gamma is your 16 kilonewton per meter cube and pi value is your 30. And this is the saturated. Now we have to ensure that there should not be any development of tension zone inside the wall, and for that we have to calculate the minimum height by which the wall has to be raised. So this is the main objective of this problem. So how we can answer this problem, that we'll see in the next slide. So we'll first convert this problem to an equivalent problem, that is this is your 5 meter. Now this added sampling, so what will it do? So it will basically impart an externally applied, or it will behave as if an externally applied surcharge on the saturated clay. So suppose this is your Q minimum. Why Q minimum? Because we are trying to find out the minimum height of the wall by which the minimum height of the sand, this additional height, the minimum height by which the wall has to be raised. So that's why this is Q minimum, and this will be gamma sand multiplied by okay. Now suppose this is the reference for Z. Now what we know, the variation of PA, this will be gamma Z Ka minus 0. Now this is valid, this expression is valid only when there is no externally applied surcharge on top of the backfill. However, this is not the case for this problem. So there is an additional surcharge which is acting on the top of the backfill. Therefore, this equation would be slightly modified, and this will be Q minimum plus gamma Z Ka minus 2C Ka. Now what is this K? Okay, so please keep in mind that this gamma is for clay. This K is for this clay, this K value is the properties of clay, okay, not of the sand clay. So this is also the properties of. Now What is the K value? What is the K value for clay? So K value for clay, this will be simply 1 because your phi value is 0. Angle of internal refraction is 0. So this is saturated clay. And what is the C value? C is 20 kPa. And what is the gamma value? Gamma is your 18 kilonewton per. Okay. And now we have to ensure that there is no development of tension inside the backfill. So for that we have to raise the, or we have to increase the height of the wall. Now we have to calculate the minimum height that there should not be any tension inside the backfill. So what should be that condition, that minimum height condition, for that there should not be any tension inside the backfill? So the variation, the active earth pressure variation, that can start from a value of 0. Okay, so we have to calculate this condition. The given condition is, as per the given condition, you can write, so H minimum will correspond to the case that PA at Z equals to 0. At most, it can have a value of 0. Okay? But it will never be, should not be negative. So it can have a value of 0 or more than 0. But for the considering the minimum condition, minimum height condition, so it can have a value of 0. So now we'll substitute the values of Z or all other relevant parameters in this equation. So then we can obtain the value of Q minimum. So this Q minimum plus 0, because we are substituting the value for Z as 0, multiplied K minus 2C root K. Okay, so therefore Q minimum, so this will be 2C. Okay. Now what is Q minimum? Q minimum is nothing but gamma sine into H minimum. Okay, so H minimum will be 2C by gamma sine 2 into 20. Now what is the unit weight of sand? So this is 60. So that means 40 by 16, so it's 2.5 meter. So this is the, so if we increase the height of the wall by 2.5 meter, then there should not be any development of tension zone inside the backfill at any point in the backfill. At the sand, for sand there will not be any tension zone, so it's the only problem in the case of cohesive frictional backfill or purely cohesive backfill. So for cohesive, since this is the second one is the cohesive case, so there should not be any development of tension zone if we increase the wall by a height of 2.5 meter, and that will be sand field. Okay, so and the sand are having the properties, the sand is having the properties 16 unit weight 16 kg per meter cube, and angle of control friction is 30 degree. So this problem was basically taken from the GATE examination 2020. Okay, so as you can see in this problem, it's not directly asked that please calculate the depth of tension crack or the negative pressure at the top of the backfill. So instead, the question is basically framed in a different fashion, that you have to calculate the minimum height by which the wall has to be raised. For that, there should not be any development of tension. Okay, so this is the trick for this problem. Now, we'll again consider one problem which is taken from GATE examinations, and this time it's from GATE 2023. So in this problem, a smooth vertical retaining wall supporting layered soils is shown. According to Rankine's earth pressure theory, the lateral active earth pressure acting at the base of the wall. Okay. So to answer this question, we can start from the top of the retaining wall, and we can proceed in a sequential manner to reach the base of the wall. But that will basically take lots of time. However, to save time, we can directly start from the base of the wall. How? So we'll see. So we'll first calculate. So we have to first check. So at what depth we have to calculate the active earth pressure. And as we can see from this problem, we have to calculate the active earth pressure at the base of the wall. And this base of the wall is basically falling inside layer 2. So therefore, the calculation of active earth pressure coefficient only for layer 2 will be sufficient to address this question. Okay. So here, it's not asked that you have to calculate the total active thrust acting on the wall. Instead, you have to answer, or you have to determine the active earth pressure acting at the base of the wall. So therefore, there is no need to go for establishing the entire active earth pressure distribution for the entire height or whole height of the retaining wall. Okay, so we will not spend unnecessary time to determine or to establish the entire distribution. Rather, we'll restrain ourselves only for the calculation of base pressure at the base of the wall. And we have checked that this base of the wall is basically falling inside layer 2. So we'll only calculate the active earth pressure coefficient for layer 2. Okay. So it will be, so Ka for layer 2, it will be tan square 45 minus 25 by 2. So it's 0.406. Okay. Now, let's check. Layer 2 is quasi-frictional. So layer 2 is C5 soil. So what will be the variation of active earth pressure? It will be gamma Z Ka minus 2CK. Okay. Now we are calculating at z equals to 3 plus 4, that means 7 meter. So at 7 meter, TA, it will be, first we have to calculate the effective work burden at the depth. So effective work burden, it will be 18 multiplied by 3, 18 multiplied by 3 plus 19 multiplied by 4. Okay, this multiplied by the earth pressure coefficient. So earth pressure coefficient of layer 2, so it's 0.406 minus 2 into C of layer 2. Okay, please be careful, it's 20 multiplied by 0.6. So it's 27 point. Okay, I did one mistake here. So I have neglected the surcharge, but that is not the case here. Okay, so here is one additional surcharge, 20 kPa surcharge. So this will also be added to the effective overburden. Okay, so 20 plus 18 multiplied by 3, this overburden is from the layer 1, then 19 multiplied by 4, this is from layer 2, multiplied by active earth pressure coefficient of layer 2, that is 0.406, minus 2 into coefficient of layer 2 into root under lateral, this active earth pressure coefficient of layer 2. Okay, so now we will see what will be the active pressure at the base of the wall. So it's 35.4. Okay, so this is the very straightforward approach by which we can save our time in the examination hall and we can answer the question. However, if you have to establish the entire distribution for the whole eye, then you have to proceed in a sequential manner by starting from the top surface of the vacuum. So first you have to establish the distribution for the layer 1, that is the top 3 meter backfill, and then followed by the below 4 meter backfill of layer. Okay, so in that case you have to calculate the active earth pressure coefficients for both the layers. So in this case, or in this problem, we have calculated the active earth pressure coefficient only for the layer 2, because we have to calculate the active earth pressure at the base. So that's why it's not required. However, in that case, you have to calculate the active earth pressure coefficients for both the layers, layer 1 and layer 2. While the resultant active thrust, you have to calculate, or you have to draw the active earth pressure distribution for the whole height of the. Okay, so this was for problem 5. Now we'll take this problem 6. It's again a problem with 2-layered subsoil or 2-layered backfill. So a 12-meter high retaining wall supports a 2-layered subsoil. The properties are given below. The water table is at a depth of 5 meters from the ground surface. So we have to first find out the total lateral force that would act on the retaining wall under active earth pressure conditions after the formation of tension crack. And the second part, we have to calculate the distance between the point of application of lateral thrust on the wall and the base of the building wall. Okay, so this is a complete means by this problem you will be having a complete knowledge, means how to calculate the total force and also its line of action from the base of the wall. Okay, so in this problem we are having layered subsoil, two layered subsoil. Also we are having water table inside the backfill. Okay, and as we can see from the properties of the backfill, that layer 1 and layer 2 both are cohesive friction. Okay, so for layer 1 the properties are the gamma saturated is 16 kilonewton per meter cube, angle of internal friction is 25 degree, then the unconfined compressive strength is 30 kPa. Okay, so from here we can easily calculate the undrained cohesion or the cohesion of the soil. So this will be Qu by 2. Then coming to second layer, the saturated unit weight is 20 kilonewton per meter cube, angle of internal friction is 30 degree, and the unconfined compressive strength, that is Qu value, is 20 kPa. So again we can calculate the Cu or the cohesion of layer 2 by dividing this Qu value by 2. Okay, and in addition to the properties of layer 1 and layer 2, the water table is same, to be located at a depth of 5 meters from the top surface of the backfill. Okay, so with this we will first calculate the cohesion of the individual layer. So for first case, first layer, so it's 30 by 2. So that means 15 kPa. Then for layer 2, it's 20 by 2. Now we'll calculate the active earth pressure coefficient for layer 1. KA1. This is for layer 1, and this is n square 45. So it's 0.406, and for layer 2 it will be 10 square 45 minus 30 by 2. Okay, so we'll introduce some notations for the calculation purpose. So suppose this height is your h1, and this is your h2. Okay, again c1, phi 1, gamma 1, These are the properties of layer 1 and C2 phi to gamma 2. These are the properties of, okay. Now we'll start determining the active earth pressure distribution. We know that the variation is gamma z Ka minus 2Ck. Okay. Now we'll first calculate the active pressures for layer 1. So at z equals to 0, the Pa value, this should be simply minus 2C1 minus 2 multiplied by 15 multiplied by root under 0.4. So it's 19.11 and 19.12 per meter square. Now since this is the cohesive frictional backfill, so we have to also calculate the tension crack depth Z0 for the top layer. So it will be 2C1 by gamma 1 multiplied by root under Ka1. 2 multiplied by 15 multiplied by what is the gamma 1 value here? So it's the 16 multiplied by 0.406. Okay. So it's 2.94 meter. Okay, so for your easy reference, so I am mentioning here what are the properties. P1 is 15 kPa, gamma 1 is 16 kilonewton per meter cube, then gamma 1 prime, that will also come into picture. Okay, for layer 1 which is below the water table, so for that you have to consider gamma 1 prime submerged unit weight, and that will be 16 minus 10 to 6 kilonewton per meter cube. Then C2 value is 10 kPa and gamma 2 prime, only gamma 2 prime, because the entire layer 2 is under or is under the water table. Okay, so it will be 20 minus 10, that is 10 kilonewton per meter cube. So these are the properties of layer 1 and layer 2, and we calculated the depth of tension crack, okay, for the top layer, and that is 2.94 meters. So at a depth of 2.94 meters, the active earth pressure will be 0. Now we'll calculate the active earth pressure at the water table, just above the water table. So that means at Z equals to minus 5 meters. Okay. Z equals to 5 meters, your PA will be, so what will be the effective work burden? So it will be simply 16 multiplied by 5. 16 multiplied by 5 multiplied by 0.406 minus 2 into 15 put under 0.40. So it is 13.36 kilometer per meter square. Now we'll come to the interface between layer 1 and layer 2, that is z equals to 8 meter. Okay, so PA, so what will be the effective work burden? It will be 16 into 5, that is above the water table, and for the remaining 3 meter it will be 6 into multiplied by 0.406 minus 2 into 15 2 into 15 into root under 0.406 plus, now we have to take the added water pressure. So water pressure for what height, so or what depth, it will be 8 minus 5. Okay, so that is only for 3 meter, then multiplied by 6. So it will be better, so if we simultaneously write the analytical form, gamma 1, okay, let as it be. Okay, so there is no need. Okay, so 16 into 5 plus 6 into 3 multiplied by 0.406 minus 19.12 plus 30. So it's 20.67. Okay, considering the first two components plus 30, that means 60.67 kilonewton per meter square. Now this is for layer 1. Okay, so this calculation was for layer 1. Now we'll move on to layer 2. Now for layer 2, we'll start from z equals to 8. So at z equals to 8 meter PA. Now you have to be very careful because earlier or so far we have used the properties of layer 1 only because we were inside layer 1. However, now we have come to layer 2, so that's why we have to use the properties of layer 2 only. So the overburden will remain same because we are at the same interface. Okay, so 16 into 5 plus 6 into 3, it will be the overburden for the interface. Now we have to multiply this overburden with the earth pressure, active earth pressure coefficient of layer 2, and it's 0.333. Okay, so this would be the change. Minus 2C. Now this coefficient again will be the coefficient of layer 2, and that is 10 kPa. Okay, then multiplied by 0.33 plus 10 into. Now for the first two components, so 16 into 5 plus 6 into 3 multiplied by 0.333 minus 2 into 10 into under 0.333. So it's 21.09 plus 30, 61.09 kilometers per square. So as you can realize, so there is a slight change in the active earth pressure, but at the same level. So at the interface between the two layers, we are having two different active earth pressures. One is from layer 1 and another one is for layer 2. Now why this change is basically happening, or this transition is happening from layer 1 to layer 2? Because or due to the change in the shear strength properties of the layers. So for layer 1, the active earth pressure coefficient was different, and for layer 2, the active earth pressure coefficient is also different. So there will be a shift in the active earth pressure at the same level. Okay, so from layer 1 to layer 2. Now we'll calculate the final level, that is at the base of the wall. So at z equals to 12 meter, you will see 16 multiplied by 5 plus 6 multiplied by 3 plus the additional overburden from layer 2, and it will be 10 multiplied by, what is this H2? H2 is 12 minus 8. Okay, so this 4 meter height. 10 multiplied by 4, so 0.33 minus 2 into 10 into 0.33 plus 10 into, now this height would be 3 plus 4. Okay, so this height, this is your this is your 3 meter, and this is your 4 meter. So this will be 10. So 16 into 5 plus 6 into 3 plus 10 into 4 multiplied by 0.33 minus 20 into 0.33. So it's 34.41 for the first two components plus 70, that means 104.41. Okay, this way, we have calculated the active earth pressure at the significant levels. Okay, now we'll try to draw the distribution. So we'll start from the top of the wall. So at the top, there is a minus pressure, and this value is 19.12. Okay, I'm not writing the unit here. All the pressures are in kPa only. So then, so this is your initial age, and this is your the remaining force. Now for 2.94, it's changing sign. This is your Z0. This is 2.94 meter. Okay, so this is 0. This is -8, and this is -12. And there it will -5. Okay, so this is your 13.36. That is the active earth pressure at the water table level. Then this value is your 21.09 at the interface. Sorry, this is not 21.09, this is 20.67 from layer 1. Okay, then there will be a slight increase. This is now 21.09 in layer 2. This is excluding the water part, water component. Okay, so water pressure part, so that will draw separately. And this component is your 34.4. Now water pressure will be added here, and this will start from at a depth of 5 meters, and that will linearly vary with depth. So at this level will be 30. Okay, so this is the active earth pressure distribution diagram for the entire height of the wall. kPa. Okay. Now we'll go back to our problem statement, because we have to ultimately answer these two questions. The first one is we have to calculate the total lateral force that is acting on the wall under active earth pressure conditions after the formation of tension crack. And the second question, we have to calculate its line of action from the base of the retaining wall. Now for the first part, so we have to be very careful about this statement, that we have to consider the earth pressure distribution only after the formation of tension. So depending on the condition, so whether it's before the formation of tension crack or whether it's after the formation of tension crack, depending on this condition, the earth pressure distribution will basically vary. Why? Because once the tension crack has been formed, as you know that the soil is very weak in tension, so there will be a separation of the soil from the retaining wall. That means there is no contact between the retaining wall and the adjacent soil mass. Now if there is no contact between the retaining wall and the adjacent soil mass, therefore it will not impart any pressure. So the initial negative portion, the initial negative portion we have to disregard. Okay. So after the tension crack, so if we try to modify this distribution for the condition where the tension crack has been formed, so it will be looking like this. So we'll start from directly from the depth of tension crack. So we'll not consider the initial tension region, because due to the separation of the soil mass from the retaining wall, so there will be no pressure on the wall. Okay, so this portion will basically disregard. Now this condition or this type of distribution is valid only when the tension crack is formed. So after the tension crack formation, the distribution will look like this. Otherwise, if we think about the distribution before the tension crack formation, we have to consider this negative portion as well. Okay, so this is the modified distribution. Due to the formation of tension crack, Okay. Now we write down the values. This is 13.36. This is 20.67. This is 21.09. This is 34.41. This is 30. Now what we'll do, we'll basically split this entire distribution into the regular shapes. So suppose this is your triangle 1, this is the 2 trapezium which is having a shape of trapezium, and this is the component 3, and the entire distribution we can take it. Okay. Now we'll calculate the area of these individual components, and we'll add these areas to calculate the resultant active thrust. Resultant active thrust EK, the summation of EA1, EA2, EA3 plus EA2. Now what's PA1? So it's half into 13.36 into 5 minus 2.94, because this height is, this is your Z0, this is your up to 5, so 5 minus Z0 will give you this height of this triangle. Okay, plus PA2, it's a trapezium, so it will be 13.36. So the sides of the trapezium are 13.36 and 20.67. 13.36 plus 20.67 by 2 multiplied by the height, and the height is 3. 8 minus 5. Okay. Now coming to the third component, it's again a trapezium, and the sides are 21.09 and 34.41. 21.09 plus 34.41 divided by 2 multiplied by 12 minus 8 plus last component, that is triangle, so half into 70 into, so this is 15 minus 12 minus. Okay, now if we calculate, this is 13.76 the second component is 51.05, the third component is 111, and the fourth component is 50. The total pressure is 420.81 kilonewton per meter. Okay. Okay, so 420.81. So this is the answer to the first part of this problem. Okay, so it's a request to all of you, please cross check all this calculation as I might be wrong in the calculation part. So now we'll move on to the second part, that is the line of action of this PA from the base of the retaining wall. Okay. Now to calculate the line of action of PA from base of the retaining wall, we'll basically take the moment of all these individual components about the base as well as the moment of the resultant. So if we take, suppose this is acting, so the resultant is acting PA at a height of Z bar from the base, and the individual components are acting at a height of Z1 bar, Z2 bar, Z3 bar, and Z4 bar, respectively, for component 1, component 2, component 3, component 4. So you can write this equation that PA times Z bar, so it's summation of PAI into ZI bar, where I is 1 to 4. Okay, so Z bar we can calculate PAI ZI divided by P. Okay, so therefore we have to additionally calculate the lever arm of all these components. Okay, ZI bars, because PAI already we have calculated, so this is known. So ZI bar, this is you have to, okay. Now once you have the ZI bars, so you can substitute those values in this equation. You can easily get the lever arm or the line of action of PA on the base of the retaining wall. Okay, so since the time is exceeded, so we will not solve this problem in this session. So rather I will request to solve this problem, or let's take this problem as a homework and solve this at your home. And while solving, if you face any difficulties, please let me know in the upcoming session. Okay, so this is a homework problem for all of you. Okay, so this is the remaining part of this problem, and it's a very straightforward thing. Just you have to calculate the individual lever arms from the base of the wall or above the base of the wall. Then you have to utilize this equation to get the lever arm or the line of action of the resultant active thrust. Okay, so apart from this homework, we'll take one more homework for this session, and this homework problem is basically taken from GATE examination 2023. So just let me read the problem statement first, and then we'll discuss a little bit about the approach by which we can solve, and we will then conclude our today's session. Okay, so in this problem, a vertical trench is excavated in a clay soil deposit having a surcharge load of 30 kPa, A fluid of unit weight 12 kilonewton per meter cube is poured in the trench to prevent collapse as the excavation proceeds. Assume that the fluid is not seeping through the soil deposit. Now, if the undrained cohesion of the clay deposit is 20 kPa and the saturated unit weight is 18 kilonewton per meter cube, what is the maximum depth of unsupported excavation? And that you have to report in meter rounded up to 2 decimal places. Okay. So this was the question in GATE examination 2023. Now, to answer this question, what you have to do, you have to again, because as you know that the deposit is clay. So in clay deposit, there is a chance of formation of tension crack. So that tension crack, so up to that tension crack, the pressure is negative. Okay. So suppose this is the Z0, that is the depth of tension crack. So for this portion, your pressure is negative. Now, for a similar height, means Z0 below this tension crack zone, the pressure will be on the opposite direction. So it's positive. Now, if we take the resultant of this distribution, that is for the top Z0 portion, it's negative, it's tension, and for the lower Z0, it's positive, it's compression. So it will basically nullify or cancel out each other. So in a consequence, as you can see, that the resultant thrust, resultant PA is basically 0. So that's why if you carry on the excavation up to this depth, that is twice Z0, you can safely carry on the excavation without any lateral support or without any confinement. Okay, so there is no need of any confining pressure or confinement, because the soil will basically stand alone without any support. Okay, since there is no active pressure or the lateral active pressure on the soil. So that's why the calculation of this negative or this tension crack depth is very, very essential before answering this question, and that we'll do in the next session. So once the depth of tension crack is known to us, so we'll take the twice of this tension crack depth as the maximum depth of unsupported excavation. Okay, so this is for today. So now I'll wait for a few minutes. If you have any questions or if you need any further clarifications, then we'll end our session here. Okay, so thanks for joining this session, and we'll again meet on next Sunday, that is on 14th April at 5 p.m. Okay, so by that time, please attempt all the homework problems which we have taken from this session. Okay, so since I am not getting a response from your end, so I am assuming that everything is fine from your side. So thanks again for joining this session and have a nice day. Okay, so I am ending this session here.